This is mini lecture number 1 for Module 6 on hypothesis testing, specifically here one sample designs. A summary of the objectives for this module is to explain what null hypothesis significance testing is, to define a null hypothesis, p-value, alpha value, rejection region, and critical value, distinguish between type 1 and type 2 errors, and to carry out and interpret a hypothesis test output for one sample t-test. So why is null hypothesis statistical testing important? Well, this is one of the most common ways that inferential statistics are carried out. So far, we've mostly been talking about descriptive statistics, so mean, median, and mode, and measures of variation, and now we're moving on to inferential statistics that are ways that we can look at the effects of treatment and see if they're significant. Null hypothesis statistical testing is a way to see if there's an effect of treatments, and one key thing with the null hypothesis is that it's a statement that there is no effect. So null hypothesis statistical testing involves establishing a null hypothesis, again, which states that there's no effect, and an alternative hypothesis, which is about some biological event that can then be tested statistically. So the null hypothesis is in general that two groups do not differ in their population means. So here we have our null hypothesis, capital H sub 0, with our two population parameters for the means and saying that they're equal. So there's no effect of the treatment on group 1 and group 0. The alternative hypothesis is that the two groups actually do differ. So here this is represented by H1. You might also see this represented by H with a sub A for an alternative hypothesis. And this is basically just saying that the two means for the groups do differ. And this gives us a testable prediction that we can use. And this is based in the thinking that if these two population means are actually estimates of the same overall parametric mean, right, the same population mean, then the difference between them should not be significant, right? There should not be very much difference between them. That should be unlikely. And so we can use a sampling distribution of the mean to calculate the probability, and this is where inferential statistics come in because they deal with probabilities, of getting a difference of the magnitude observed between these two sample means due to chance. So we want to know if there's differences in these values of mu1 and mu0, what's the probability that that's just due to random chance versus being some biological event. And so if the probability is low enough that the difference that we're seeing between these two means is likely due to random chance, then we can reject the null hypothesis and say that something biological is likely causing the difference that we're seeing. And so we know from what we've already covered in this course that when we collect samples from a population, there's some variation in the values, and we take this into account when we do statistical inference. So the general steps in statistical inference is to, first of all, construct a statistical hypothesis, and this is what we're thinking if something is only due to sampling error. So here's a distribution of t. If the null hypothesis is true, it's centered around 0 with some variation on either side. And according to the null hypothesis, the only source of variation could be because of sampling error. It's not because of anything biological that's going on when we're looking at the null hypothesis. Often the null hypothesis is not of biological interest. It's just giving us a basis for comparison. So in addition to characterizing the variations solely due to sampling error, we can also consider possible distributions if something interesting was actually happening. So in this case, we see a shift to the right of the distribution for the value of t's if our null hypothesis is false. And here we see that positive biological effects will result in a larger value of t. And stronger effects will end up with even larger values of t. However, it is also important to note that when we see that the null hypothesis is actually false, part of that distribution of t has very small values, and that can just be due to sampling error, even if the null hypothesis is actually false. The second step is to establish a statistical decision rule, And this is taking into account what we just looked at, in that large values of t should occur rarely just due to sampling error. So if we have some observations and they result in a value of t larger than some particular value, which we're going to call a critical value, so that's our cutoff, we decide that the result is reflecting something that's interesting biologically and not just sampling error. And this is related to alpha, and this is also known as the type 1 error rate, and it's the probability of rejecting the null hypothesis when it's true. So in that case, that's suggesting that there wouldn't be any difference between the means. So often we set this at 0.05 to say that we're willing to accept that there's a 5% probability that we're going to say there's a true difference between the means when there actually is not. And we'll come back to type 1 error in a little bit. The third step is to calculate this test statistic. So we've identified our decision rule, so we're going to collect our data and calculate our statistic. This is an example of a one-sample t-statistic where we're comparing a sample mean that we have to a known population value, which is represented by mu sub 0. We divide that by our standard error. And you know the calculation for standard error, it's the standard deviation of the sample divided by the square root of n. And you'll see in this course a number of different test statistics. And then the fourth step is to compare the test statistic with our decision rule and draw some statistical conclusion about our null hypothesis. And either we're going to retain our null hypothesis based on the data, or we're going to reject our null hypothesis and accept the alternative hypothesis, which, as we were looking at, was stating that there actually is a difference between the means. One important thing to note is that we cannot conclude that we have proven the null hypothesis. All we can do in statistical testing is disprove hypotheses. But if we accept the null hypothesis, that doesn't mean that we've proven anything. And also, as I mentioned earlier, that sometimes we can get values of our t-statistic that are maybe less than our critical value just due to sampling error. So there could be something biologically interesting going on, but there's so much sampling variation that our value of our t-statistic is less than our critical value. So a few terms that you should know. One is the p-value, so that's the probability of the data observed if the null hypothesis is true. The type 1 error rate is what we call alpha, and it's the probability of rejecting the null hypothesis when it's true. And the type 2 error rate is also known as beta, and it's the probability of accepting the null hypothesis when it's actually false. So when we look at type 1 and type 2 errors, we have this table that's quite common to see, and it has the true situation in the population and then the decision made on the sample data. And if the null hypothesis is true and we retain it, then we've made the correct decision. If the null hypothesis is false and we've rejected the null hypothesis, then we've also made a correct decision. However, there might be situations where the null hypothesis is true and we've rejected it, and that's our type 1 error rate, or alpha, which is often set at 0.05, meaning there's a 5% chance that although we've rejected the null hypothesis, it's actually true. And then our type 2 error is when we've decided to retain the null hypothesis, but it's actually false. So we can diagram this out to look at these type 1 and type 2 errors. And we can do this by drawing a distribution of t-values. And this is going to be if the null hypothesis is true. Right? So we're looking at a distribution of t. And we might have some critical value that we're going to assign. And that would be our critical value to determine if there's a difference between our population means. So we have another distribution here that's representing what we would expect if the null hypothesis was false. And say we have our critical value of t. Okay, so this is based on our statistical decision rule. Now when we look at this, we have a distribution for the null hypothesis being false and a distribution for the null hypothesis being true. Now, where this critical value is, there's some data from the distribution where the null hypothesis that's true that falls to the right of our critical value in this case. And this, the amount of data that's contained in there is alpha. And alpha is our type 1 error rate, and it's 5%. We also see that under our distribution where the null hypothesis is false, a lot of that falls to the left of our critical value. So this is when the null hypothesis is false, but if it's to the left of our critical value in this case, then we would say that the null hypothesis was true, which would be what we would decide. We would retain it. So this is our type 2 error, or beta. Right, whereas our alpha is our type 1 error. And then the rest of the distribution for where the null hypothesis is actually false, and we're saying that it's false, well, we have beta on this side, so the rest of it over here is 1 minus beta, and we call that power. And that's when we've rejected the null hypothesis, when the null hypothesis is actually false. So when we think about where these errors fit, that's how we put together the alpha, the beta, and power.